Okay, so today we talk about polar coordinates, and by we, I mean me, because this is online learning. Yeah. I wish you were here so that we could talk together about polar coordinates. And it's what you need to do question 1 and 2 and so forth. So the first step is you need to know how to convert polar coordinates to Cartesian coordinates and back and forth, and so you need to know what polar coordinates are in the first place. So polar coordinates is a point in space is given, meaning two dimensions. A point in 2 dimensions is not given by its Cartesian coordinates, but let's review what a Cartesian coordinate is. Cartesian coordinate is you have an x and a y value, and so you address this point by its ordered pair. That's Cartesian coordinates. However, if instead you want to address it differently, you say, well, first of all, what is the angle from the origin to the point? I'm going to call that theta. And what is the distance? So you can think of somebody in the middle swinging a ball on a rope, swinging it around and around and around. And as theta changes, the length of the rope changes. You might pull in on the rope or let out on the rope, and it changes the path of this, makes like a different path somehow. Okay, so we know what we already know about the x squared plus y squared equals r squared formula. Pythagorean theorem. And so if you already know x and y, you know r. So r is equal to the square root of x squared plus y squared, and we do not have to worry about the negative square root because we only use positive. Well, we don't always use positive radius. I just lied to you. Yeah, so in the beginning, we just use positive r. Let's just put it that way. Okay, now let's figure out how we would find theta now. What would theta be? So what do we know about x, y, and r? Theta is angle whose something is something, right? So what do we know? We know sine of theta is y over r, and so forth, but we need a relationship that just has x and y in it, so it must be tan of theta is y over x. So if you want to just ask for theta directly, you can say an angle whose tangent is y over x. So therefore you have r as a function of x and y and theta as a function of x and y. And I guess we probably need x and y as a function of theta and r as well. So let me just change colors for that. Let's see, x would have to be what? R times sine of theta would have to give us x, right? Because y over r is sine of theta, and x over r is cosine of theta. So together with these two formulas and these two formulas, then you can do the conversions that you need to do. Okay, so let's do a couple examples. Let's just make something up. If we have a Cartesian coordinate right there, may as well stay in quadrant 1, and it's 1, 1, and those are the Cartesian coordinates, right? So this is like I would just put Cartesian coordinates. Then what do we have for r and theta? So it turns out, well, the radius has to be square root of 1 plus 1, so square root of 2, because I'm just using this formula. And theta is an angle whose tangent is 1. So this is going to be 45 degrees, or if you prefer to use radians, it's going to be pi over 4. Okay? And so if you're writing it as an ordered pair, you can do this sort of thing. I don't tend to do that, but you can. It's just kind of confusing. And you can see on the worksheet, if it's going to be written that way, it's r equals whatever, theta equals whatever, spelled out very explicitly, because typically when you just see an ordered pair, you're going to assume it's x and y. Okay? All right, so let's do another example. What if instead we're looking for x and y, and we are given r is equal to 5, theta is equal to pi over 3, and I just made this up right out of my head. So then x is going to be r times cosine of pi over 3, and y is going to be 5 times sine of pi over 3. Well, what if you don't remember what sine and cosine of pi over 3 is? Well, then you're in good company. Lots of people forget this stuff. So it's going to be 60 degrees. Let's see, it's going to be looking like an equilateral triangle. Let's see, theta, you're going to have a 2 here, a 1 here, a square root of 3. Cosine is going to be x over r, which is 1/2, so you're going to get 5/2. I'm just ignoring this other half of the triangle, of the equilateral triangle. Sine is going to be y over r, which is square root of 3 over 2. There we go. So now I can get rid of this little triangle. Okay, so you can also just look these up on Wolfram Alpha. It's good if you at least know how to do it in a pinch. I don't mind if you use technology for things that you're just being lazy about, but please do not refer to Wolfram Alpha to do things that you don't actually know how to do. In that case, ask me how to do them, because that's what we're here for, is to learn. Okay, here's a very crazy question. What is the x and y? What is the x and y pair if r is -4 and theta is equal to pi? So the idea would be you would think, okay, theta is pi, so you're shooting off in, hold on. I hate when that happens. Okay, so you're shooting off in this direction, except that you're not. I'm lying to you because I put a negative. So I'm really going off in the opposite direction, and so I would be at 4. So the ordered pair would be 4, 0. So that's all. So if you have a negative r, you can just essentially add pi to your theta and keep going with your life. But just beware of that. That's how that flip-floppy thing works. Just in case you've forgotten how some of these angular conventions work, when you start opening up your angle, this would be like the smallest, tiniest little angle. And then the next angle would be here and here. You open up in this direction. That's the order. You just go, that's your positive direction. Okay? And so just keep that in mind. That's really important. Okay, so what if I want to know the inequalities? So what are the inequalities that represent this sector? So this is similar to one of the ones in your worksheet. I'm going to let you figure out the first two by yourself. But in this case, r is between 0 and what? I don't know. So what is r? Well, we have x squared plus y squared, and then we take the square root of that. So that would be 4 square root of 2, I guess. So this sector goes from 0 all the way out to 4 square root of 2. So I guess this right here would have to be minus 4 square root of 2. And then we have to figure out what the angle is. And that should be a little easier. So this is going all the way to pi, and this is half a pi, or 2/4, so 3/4 pi up to pi. And I guess these are equal like that. It doesn't much matter. Okay, so that's how you figure this out. You just figure out what area is filled in, and voila. And what about an exercise like this? What are the inequalities here? Well, the radius is going to be greater than 4, greater than or equal to 4. That means everything on this bounding line and beyond. But what is the theta? It's between something and 2 pi. So it's minus a half. So I guess it's 3 pi over 2. Yeah, that sounds about right. So you just figure out what the thetas are, and you figure out what the radius is, and there you go. Okay, so in order to find areas in polar coordinates, if you're just a formula person, you can memorize the formulas. But this, you probably know me by now. I'm not like that. What is the area of a circle? A circle is pi times the radius squared. So this part you should memorize. So, I mean, we could derive it, but we're not going to do that today. If you have a little piece of curve and you want to know the area of this wedge, and there's this sort of bounding curve, and then this is r is a function of theta, how would you find that area? So when you have Cartesian coordinates, everything's nice, so you just integrate the function and you've got it. It's a little more complicated because you have these little wedge-like shapes that are forming. You're forming these little triangular wedges whenever you're moving along your curve. Okay? And you want to be able to capture that somehow. Now, I want you to think what happens if this r is constant. So for one little tiny wedge, you can imagine that for a moment, the r is just a number, and that you're just taking out a sector. So you go back to your exercises from question 2, and you think about that. What portion of a circle is represented by a little wedge theta? Well, theta, if that theta is 2 pi, it's the whole circle. So this is the ratio of the circle, and the circle itself is pi r squared. So this is the fraction of the circle that is being represented by this little d theta, this little tiny d theta strip. Okay, and so nicely the pi's cancel out, and so then you get see, r is actually a function of theta, and you're going to square it, divide by 2, and that little r piece, what is it? We actually call that d theta, because that's this little tiny piece of d theta right here, and we're going to integrate over whatever relevant lower and upper, the lower and upper thetas we're interested in. So that's what we're going to look to do. And let's go ahead and make up an example. Okay, I'm just messing around with Desmos here, playing with polar curves. And one of the neat things with Desmos is you can just pick a piece of the curve to plot. So if I just want to go from, say, I want to see where this thing starts, I'm going to go from 0 to 0.2 just to see how this curve is developing. So I don't really know what I want to do with this. I'm just playing with it literally, but I wanted to show you that you can just sort of slow-mo this to get a sense for what's going on here. Does it let me do pi? Oh, that's lovely. So this is really cool. So if I just go from 0 to pi, I see this beautiful curve. And what if I wanted to find the area inside this? Well, the curve is actually moving kind of backwards, but I think we could still do it. Maybe my goal is to just find what's inside this little loop-de-loop. All right. So this little loop, I don't really know where these things cross, and that's where I would have to work at this. Okay, so essentially what I want to do is, this is just a numerical guess. I'm going to have to figure out where that really is, and I'm going to try, I will figure out where this is and where it actually crosses, and then I will attempt to find this much of the area, and once I do, I can double it to find the area of the whole loopy-loop. Okay, so let me pause while I strategize for a second. Okay, I think I have my strategy. So I want to find the area of this whole little loopy-doop, and so it's, I don't know how big it is or where it ends, but I'm really only interested in going up to pi over 2. So pi over 2 is, let's see if I can do this. Oh, wonderful, beautiful. Okay, so that gets as a get out of jail for free card. But I'm going to go ahead and plot this on Desmos again, but just 4 minus 6x. So Desmos seems to recognize that I want Cartesian coordinates when I use an x. And so really what I'm looking at is this point here, this 7, 3. And so it's not really helping. So I went over to Wolfram and said, could you please give me a better look at what's going on? And it was the obvious answer, which is t is just an angle whose sine is 2 over 3, which is kind of pathetic and obvious, but that's just okay with me. That's all I'm looking for. So I'm going to actually just integrate this mess, and I'm going to show you what I was thinking when I was sketching this out. I said, well, I'm going to say if x is equal to, is going to go from the lower end, is going to be arc sine of 2/3, because that's what Wolfram said the answer was, and I'm going to go up to pi over 2, but I want the whole loopy-doop, so I want to double that, okay? And then I'm going to put inside here the actual function, which is 4 minus 6 sine of theta, and I'm going to square that, but the 2's are going to cancel out, so I don't need these 2's anymore. I don't need this divided by 2. And so then again, I'm being lazy, judiciously lazy, and I'm going to just dump all this into Wolfram Alpha, and Wolfram Alpha says that that's going to be about 1.764. So Wolfram says this whole thing is about 1.764, and if you really want the gory details, Wolfram does give you the actual answer, which just looks horrific. So I'm just not going to copy that down. Okay, yes, I could do that. It's just not worth my time. So I'm just going to go ahead and let the computer do that. But a lot of these questions you're going to be asked to set up but do not calculate. Okay, I really want you to get the conceptual understanding of what you're doing, and if you use a computer assist for some of the messy arithmetic or integration, that's fine by me. So I guess some of the tricks you want to learn is that you really want to plot these things on Desmos, but also plot the Cartesian version just to get your bearings, because when you're plotting when you're plotting something in polar coordinates, you often lose sight of things like, well, the negative problem. There really is a problem with negatives, because this point, for example, right here, did you get there from a negative r or a positive r? Do you even know? And so it's very often useful to just look at the Cartesian version of the same plot so that you can figure out where all the pieces came from. For your actual exercise number 4, you're supposed to find the area inside the cardioid. The light blue is the cardioid, and the circle is the dark blue. And so you want the area outside of the circle, but inside the cardioid. Now you may think that your life was just made miserable, but it was actually to make your life less miserable, because all you have to do is find this angle, find out where they intersect, and then you're going to You don't need to integrate as much as you think you do. It's just to actually make things way easier for you, because otherwise you're going to have to figure out the same curve twice. I mean, it's just going to be a mess. It could be a mess. Anyway, it just makes your life easier, because then you have to just draw this line, and then you can just do like half of this and double it. Just because you're listening, I'm going to give you a clue. When you find the intersection, this angle has a pi in it. Pi times an integer divided by 6. I mean, you're going to have to figure out what that numerator is, but it's times pi over 6. It's a multiple of pi over 6. So if you don't get a pi and a 6 in your intersection point, then you did something wrong. Okay, and last but not least, you're going to be asked to find the equation of the tangent, of the line tangent to some things. Okay, so r, in your case, r is equal to theta. So r is a function of theta, and it's theta, and it's at theta equals pi over 3. So that means also note, of course, r equals pi over 3, because r equals theta. Okay, so what does this thing look like? Wolfram. Okay, Desmos also does a beautiful job, I admit. Okay, but what we're looking at is, it just looks like a cinnamon bun. That's really all it is. Or a roll of toilet paper, whatever you want it to be. It's not that exciting. So r of theta equals theta. You are literally looking for a tangent line at pi over 3, and where is that? It's somewhere on this little hook. How about, let's just plot it from 0 to pi over 3 so that we can just be sure where that ends. So it makes sense to us. Okay, so that's it. We want to find the tangent line right here, and I trust you to be able to find the x and y values that go with the end of this little point here. And then you can just sort of sanity check it against this plot. Now, the thing you're going to have a little trouble with is you're going to say, okay, so in order to find a tangent line, I need a point and a slope. So how do I find the slope in the Cartesian world if what I have is the formula in the polar world, right? Okay, so to find the equation of the tangent line, you need a point, but then how do you get that slope? That is your big question right now. Okay, so let's think about this. You know that x is equal to r cosine theta and y is equal to r sine theta. But what is r? R is a function of theta. So r is a function of theta. Okay, r is a function of theta. You know what it is. For this specific problem, it's just theta. But now you can take the derivative of x. So you're going to take the derivative of x with respect to theta, and you're going to take the derivative of y with respect to theta. And if you like, you can, theta could be t, so you could just use x dot and y dot if you're being lazy. Okay, so how do you find dy dx? Hopefully you figured this out already, but what you do is you stack them, right? So you do dy d theta over dx d theta, and then you evaluate it at the theta you've been requested. Evaluate, yeah, line please, at theta is equal to whatever it is, wherever it is you want to find that tangent line, and that's going to be the slope of your tangent line. Okay, it seems really complex, but that's how you do it. I will warn you that this is one of these things that's conceptually trivial, but it does take like half a piece of paper to work it out. So don't get stressed out about that. It will take paper. Don't worry about it. You're going to have pi's and square root of 3's in there and some negative numbers. Don't worry about it. Just push through it. If you get really tired of it, get some technology assist. But it's again, it's just annoying. It's not actually difficult. All right, so have fun with that, and I'll see you soon.